This lecture is about synchronous generator ratings. When we talk of synchronous generator ratings, we are talking about the limits that the generator has with regards to speed and power that we can achieve. So when you have a generator that is rated to a certain number of kVA, we can only be able to output a certain amount of power from that generator. And this topic will describe what we call the capability of the generator, and we will then draw the capability curves of the generators themselves. So let's begin. So the factors that affect the amount of power that can be drawn from a generator are, so for example, we have speed and frequency. The speed and frequency are limited by the rotations that the prime mover of the generator can achieve. So you will always have FE is equal to NMP over 120, where F is the frequency, N, of course, is the mechanical speed, and P is the number of poles. This is a fixed relationship depending on the number of poles of the generator. So you cannot change this during the operation of the generator. Secondly, we have the voltage. Of course, the limitations of the generator do not allow it to produce a voltage beyond its construction or design. So we talked of the induced internal generated voltage is equal to a factor K due to construction times the flux, which is the field, times the speed of rotation. Okay, so these three are the factors that affect the amount of voltage that you can supply. Now, there is the voltage itself is generated in relation to IF, which is the field current. This is what we had already talked about in previous lectures, that the voltage is controlled by the field current that is supplied to the generator. And the field current itself, of course, has a limit. It is limited to the current that the conductors can carry. So a maximum IF, right? The field conductors have a certain limit as to the amount of current they can carry. If the limit is exceeded, the cable in the field windings will melt. Right? So one of the key elements is field current. Right? In addition to that, the voltage itself has a limit in that the value of the voltage must not exceed the limits of the insulation within the windings of your armature. So EA must not exceed insulation limits. Right? So those are the two limitations to do with voltage. So voltage is indirectly affected by the field current, or it's directly proportional to the field current. So there's a limitation on the maximum field current that you can have. At the same time, there's a limitation on the maximum voltage that can be present within the machine. Number 3 would be power. So there's a limit to the amount of power that, first of all, you can apply to the machine, and secondly, you can take out of the machine. So in terms of input power, this is limited by the prime mover. So the input that you can put into the generator is limited by the prime mover. If your engine cannot operate beyond a certain amount of kilowatts, that is the limit of your prime mover, and this is measured in kilowatts. Likewise, your generator has a maximum heating that it can sustain. So the synchronous generator cannot supply power beyond a certain limit because there's a limit on the stator current. Okay. And therefore, the overall rating that you would receive for this is a rated power. So the armature current determines the amount of kVA that you would be able to get out of the generator. Usually, that is the upper limit of power within your generator. And then number 4, we have power factor. So there's a limit of the power factor that the machine can be able to supply. So now let's look at some of the elements that we are talking about. So let's say you have your generator with a certain VT, terminal voltage, and you have a current IA operating at that point. Now, in this case, VT and IA are the currents and voltage that you see being supplied by the generator. So internally, you would of course have your generator having an internal property that looked like that. So at 90 degrees, you have JXSIA being applied there. And of course, you'd have EA over there. So let's just extend that, right? And you have EA, okay? So now the limits that you would have depend on various characteristics. So first of all, let's say that you are supplying IA at a maximum value of that current. So that IA maximum is the maximum current that the generator can actually supply, which means that this vector is the maximum vector that you can possibly have with regards to that generator. So that if we were to change, for example, the power factor, let's use a different color. So if you change the power factor, you maintain IA max at the same level, but you change its angle so that you have various points. It would form a circle around that point. The magnitudes of all these are equal to IA maximum, right? We are taking the maximum current that can be drawn from that generator, but we are changing the power factor. So changing power factor, but you can have the constant at maximum IA, right? That is the locus of the current that will go through. That would mean that there would be a corresponding locus over here for your voltage that is on this side, right? So your limits in terms of current would be having a corresponding set of these values of JXSIA max, right? As you change the voltage here, as you change the power factor here, you would have them changing similarly in that direction, because they are always at 90 degrees to each other. They're always perpendicular to each other, right? So that is the locus of one of the limitations. A second limitation would be, let's redraw it slightly. So this is limit of power factor. Second limitation that we would have is if we had EA at maximum, the maximum internal generated voltage. Remember that maximum generated voltage is dependent on the value of field current. Yeah. So the limit of the field current and the limit of the insulation determine the maximum internal generated voltage. Whichever of those is lower. And generally, the limit of field current will be reached before the limit of insulation of the machine. So the factor here is the maximum field current that you can have. So in this case, let's assume EA max is there. The value of EA max would go along a locus centered on here. The only change you could have is your angle of the phasor itself. So that means you'd have your locus looking something like that. So the value of EA would move along that locus, right? So this is the limit of field current IF, and by extension, the limit of the voltage. So now let's redraw this in order to understand a bit more about the phasor diagram. So we will draw a set of axes here. Let's talk about those being in volts. That's also in volts. And what we will understand here is that you will then have you will then be able to understand that the phasor that we are having here can be broken down into its components looking like this, right? So that we then have XSIA, if this is theta, you have XSIA sine theta. And if this is cos theta, you'll have XSIA cos theta, right? Now, what you will note from here is that on these vertical axis, these are real components, and on that vertical axis, here we have reactive components, right? So you can break down the powers of this generator into those components. Now, the value of power, that is real power, produced by the generator is given by 3VT IA cos theta, right? The theta which we have here, okay? Now, that particular angle is interesting because you can do a slight modification to the formula or to the equation, and it will be P is equal to 3VT. Let's do XS over XS. Let's do an alteration to that, and it will be times IA cos theta. What this will then become, if you further modify it, it will be 3VT over XS times XSIA cos theta, right? Which is what we have here, okay? We have already seen that in this diagram, we have that XS cos theta already indicated, XSIA cos theta. Similarly, for Q, which is the reactive power, you will have 3VTIA sine theta. And if you undergo the same conversion, it will be 3VT over XS into XSIA sine theta, right? Which in our diagram is represented here. Okay, so what this means now is that if you want to change this phasor diagram from units of voltage to units of power, let's say kVA or kVAR, you would then have, this would be kVAR, and this would be kW kilowatts, right? You would then be able to convert them simply by using the conversion factor of that, right? That is a factor that you can use to convert among the two, from a voltage current phasor diagram to a power diagram. You multiply it by a factor of 3VT XS. And what you'll end up with is the equivalent diagram, but for power, and it will look something like this. If you have two sets of axes, straighten it up a bit. You have your axis there, your axis there. So you would then have, for power, you would have your angle here, or your first phasor here, which is VT, the equivalent of VT in terms of power. And you would have your angle on that side. And you would then have a phasor equivalent to VT or to EA, which we call DE. Right? That's our equivalent angle. Here, you would then have your angle theta. Okay. Now, theta here, of course, is the same as this theta here, right? Which is where we got this theta. Okay. So now here, in this case, we have Q, which is 3VT IA sine theta. And you have 3VT IA cos theta. Right? With the conversions, we can then state that you would then have, at this point VT, this particular angle, or rather this particular vector, would be equal to Q in VT XS into negative VT, because this is the factor that we use to convert those voltage current phasor diagram into a power diagram. So that means Q is equal to negative 3VT squared over XS. And similarly, for DE, you would have our vector here, DE. You would have 3VT over XS into EA. Okay. And S, which is here, S would be equal to 3VT over XS into IA XS, which is equal to 3VT IA. Right? So those are the main components of your phasor diagram converted to a power diagram. Now, what you would then notice is you have in this particular position, you would have the locus of the various items which we had already discussed. So the locus of DE would move along here. And likewise, the locus of S would move as a center along there. So it would be a circle centered around that particular area. That's not a very accurate circle, but those are some of the limits that we would have. So what you would notice is this locus represents the limit of field current. Which we had previously indicated. And this locus represents the limit of stator current. So those are the two main limitations which we have already discussed here. So the limit of power factor, which is the limitations of IA max, and also the limit of field current, which gives you the limitation of your internal generated voltage, which was here. The locus was there. So now we have combined these two into our power diagram, and it shows us the limitations of those two. So it means our machine can only operate within this quadrant. It cannot exceed this area of operation, right? Beyond here, it exceeds the limit of field current, and beyond this circle, it exceeds the limit of stator current. So the safe values of power that it can generate will be indicated by these points that are here. And you find that the axis here, we had said is kVAR, so that is reactive. So these are the values of Q that you can have, and these are the values of P that you can have, real power and reactive power, right? So now it is conventional to have this diagram, the axis flipped, so that the P axis is horizontal and the Q axis is vertical. And in that case, we would then have a diagram that would look like this. So let me just switch to a diagram of what it would look like. So there now we have what we call the capability curve of a particular machine. And here we can see the three limitations that we have talked about. So here IA limit is the limit of the stator current. Here IF limit is the limit of field current or voltage, internal generated voltage. And now we add a third limit, which is the limit of power, which we mentioned as the limit of the actual prime mover. So your prime mover has a limitation to the amount of kilowatts that it can put into the generator. So you might find that even though the stator itself can carry current beyond a certain level, the prime mover may not be able to supply it. So if we zoom out, we can then note that you have your angle as indicated here, or rather your dimensions indicated here. This Q point was the center of the phasor diagram that we had drawn previously. So if we go back to that diagram, it represents the center of the phase diagram that we had. Second. So it represents that point, that radius, Q point. Sorry. Q point. That is the center of the circle that represents the limit of field current. So if we cut back to that, all right, this Q point is the one we are talking about as the center of the limit of field current. The locus of the circle indicated is where we are. So now what the generator can supply is the area within this particular part, the intersection of these three limits. So there's a line limit of physical power, there's a circle limit of the field current, which is the voltage, and there's a limit of the stator. Now practically these ratings are indicated through these four quantities. So you have rated voltage. Now you can see what happens when we play around with rated voltage. you notice that the circle of field limit is smaller and smaller. So if the limit of current is smaller, the rated voltage is smaller. If the limit of field current is higher, you can have a higher rated voltage. Similarly, the two ratings that are there, the power that can actually be in the machine is related to both of them at the same time. So you would then have the value of your stator current. If your machine can carry a rated power that is much higher, the value of the stator current that can flow would be higher. But if it can only carry a small stator current, you would see that it would only be able to have a rated power that is very small. So we can take that back there. And similarly, your prime mover limit is reduced. So if you have a very low powered prime mover, in this case, say 20 kilowatts, the area in which it can operate is only within this point, right? It can only operate at that level. So once again, the x-axis represents the real power and the y-axis represents the Q power. Notice that we have rotated it on its side and reflected it, so that on the right-hand side, we are generating real power. On the left-hand side, we are consuming it. So in the real sense, your generator would only operate on this area in the right-hand side. It can have a lagging current, which is above, or a leading current, which is negative. That is, it is consuming, right? So those are our various limits in terms of generator capacity. So in order for us to do it, to understand it a bit better, let's work on an example. So let's give an example. So now let's look at an example to demonstrate the capability curves. So a 480 volt, 50 hertz star connected 6-pole synchronous generator is rated at 50 kVA. It has that synchronous reactance. We assume the generator is connected to a steam turbine capable of supplying up to 45 kilowatts. And then those are the losses, 1.5 and 1 kilowatt losses. So the maximum current that the generator can generate will be given by the value of S rated being equal to 3 VT IA max, right? It will be obtained from that relationship. So our VT will be given by the voltage. Now this is star connected, so VT at the terminals, the phase voltage at the terminals, is 480 over root 3, which is given by, let's bring out the calculator. So it's given by 480 divided by root 3, which is 277.13 volts, right? Therefore, the maximum current IA max is equal to the rated kVA, which is 50 divided by 50 times 1,000, because it's kVA, divided by 3 times 277.13, which is 60.14 amperes. So that's our maximum stator current, right? Now we may now be able to draw our capability curve. So we start off, so let's look at capability curve. So to start off with, let's look for Q. So Q is given by that formula we talked of, negative 3 VT squared over XS, which is negative 3 times 277.13 squared over 1 ohm. So 277.13 squared times 3 is equal to that. So it is negative 230.4 kVAR. So now EA maximum will occur when IA is also maximum, which we had indicated here earlier. So it is 60.14, right? At this instant, you will have EA and IA looking like that, right? So EA is here, and then you have your IA at maximum, which gives rise to JXSIA maximum, right? Now VT is here. So now this theta, when IA is maximum, is equal to that theta when IA is maximum. So this is there, okay? Now, what then happens is you have EA when it is maximum will be given by EA and JXISIA. So VT and JXISIA maximum will be your value of EA when IA is maximum, right? So what we then have is EA is equal to VT, which remains constant, plus JXSIA at maximum, right? Remember, IA at maximum is taking place, it is 60.14 amps, and it is taking place when your rated current is available. So that means that if you go back, the rated current is available at 0.8 PF. So that means that the cos theta in this case is our PF, which is 0.8. That then gives us as theta will be equal to cos inverse of 0.8, which will help to give us the angle of our theta. So that is equals 36.87 degrees. So that's the angle. So what we then end up with is EA at maximum will be VT, which is 277.13. We already calculated that. Plus JXS was 1.0 ohms. That is the synchronous reactance. Times IA, which is 60.14 amps. 60.14 amps at an angle of 36.87, right? So our IA here is at an angle of 36.87. But remember that it is in a negative direction, so you still have to put your negative here. 277.13 plus 1I times 60.14 into negative 36.87 degrees. And that gives us which is 316.8, let's call it 89 volts at an angle of 8.73. Okay, so that is our value of EA at the maximum possible angle. So this was done in order that we can get our DE, which is what we will need when we are drawing our capability curve. So DE is equal to 3EA times VT over XS. So it will be 3 times 316.89 times our VT was 277.13 over 1. So it is 3 times 316.89 times 277.13 0.13. So that means it is 263.46 kVAR. Okay, so we now have two components of your capability curve. You have your Q there, and you have your DE, which is there, right? So now what this means is you then have your capability, but before we move to the capability curve, let's look at the maximum output. So one more thing we need to do is maximum output, which is given by maximum input from the generator minus mechanical losses minus core losses, right? So maximum input from the generator was given by 45 kilowatts. So 45 kilowatts minus mechanical losses, which were 1.5, and the core losses were 1. Minus 1.5 minus 1. So 45 minus 1.5 minus 1. So this is 42.5 kilowatts. Right. So this is our maximum output. Our limit of the prime mover, what we can actually get, is limited by that. Okay. So now if we draw our capability curve, let's just have some squares that will guide us, something like that. And if we have your capability curve, we zoom out a bit, we have it so this is our P axis, this is our Q axis. Let's zoom in a bit, and let's take the scale to be in terms of 25. So 25, 50, 0. Let's move this slightly. So this is 25, 50, 75. Right. So going back to our indications. So the first thing is we look for the field current limit. So the field current limit is a circle centered around the Q point with a radius of DE. So DE will be our radius, and Q, the Q point, will be our center, right? So our center is at negative 230.4 kVAR. So negative 230.4 kVAR. Let's have it here. 230.4 would be roughly somewhere there. So negative 230.4. Okay. And then it has a radius DE of 263. So that means that it has a Q intercept. So the point at which it intercepts Q intercept will be equal to 263.46 minus 230.4. Okay, let's bring back our calculator, and our value will be given as 33, right? So it's equal to 33. So we will look for a point here which is at 33, which should be roughly in between. So let's call it there. So 33, right? Now, this point is the Q intercept of a circle that has its radius here. So it's a huge circle that will, it is an This q-intercept is a circle that has a radius that is crossing the q-axis at that point. So it will move something like that. And something like that. Okay. And this is our value of field current limit. Field current limit. Right. Next, we look for the stator current limit. And the stator current limit is the limit of the generator itself. So how much power can the generator itself generate, which is 50 kVA. So we will have a circle with a radius around the center of 50 kVA. So it can produce 50 kVA in any direction. So it will look something like that. Best circle that purpose. Okay, and this is our stator current limit. Okay, IA limit, and the other one was IF limit. Okay, and finally we will look for the prime mover limit, which has been indicated by the maximum output that we can have, which is 42.5 kilowatt. The reason for that, of course, is prime mover limit is 45, but you also have to account for mechanical losses and core losses. So the actual maximum power that you can the useful maximum power that you can have is 42.5. So it will be somewhere around here. Let's call it there. And then it will be shown by a straight line along that point. So this is prime mover limit. Right? And there we have drawn our capability curve. So that means that our generator practically will be able to supply any value of active or reactive power in this particular area. So the limit is there, 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 and there. That is the limit of our generator's capability. Okay, and there we have the capability curve example, and I think we can stop there.